So for the first question, where we are going to aggregate the data and calculate the macroscopic traffic flow, I did it uh, on positron here with the R programming language. So the data that we have here in the table, which has these 4 columns, I have put them in a data frame. And if I load the tidyverse, which contains the packages for data manipulation and analysis, for the first part of the question, we are going to first create a data frame, and I'm calling it df, very creative of me. And then running view df would show us the data. So here's that same table. Our goal here is to use this single vehicle data and then look at macroscopic quantities. So if we, for example, look at the macroscopic quantities by lane, I can add filter here and then select only the lane 1 here. Lane 1 is, according to this, the right lane, and lane 2 is the left lane. So what we want to do is estimate the traffic flow and also estimate the speed. And the speed should be the arithmetic mean speed, which means just take the average of this thing. So that's exactly what we do in the next step. We take df, and then in R, this is called as a pipe operator, which means and then. So we take the data frame and then we group it by the lane column. In this case, that's this column. And then once we have done that, we then summarize and estimate the flow and the macroscopic speed. The speed, as we discussed, is going to be the arithmetic mean, so we just use the mean function. And since we are doing it by group, we can do it for each lane separately. And for the flow, we use the definition of the flow, which is the number of vehicles passing a particular cross section within the time interval. The time interval which is given to us in the problem is 30 seconds right here. So we use exactly that. And we convert it into vehicles per hour. So we use the n and then parentheses function in R that stands for finding the number of rows. This is a function from the dplyr package, which is part of the tidyverse package. And then we use this conversion factor to convert it into vehicles per hour instead of vehicles per second. And then in the next step, we also need to estimate the traffic density. Um, so that is in number 2. Calculate the traffic density in each lane, assuming that speed and time headway of 2 succeeding vehicles are uncorrelated, which is realistic for free traffic. So the assumption here is that given the speeds that we see here, these are free traffic conditions, and we can now estimate the traffic density using the hydrodynamic relation, which is rho equals to Q over V. If you remember from our previous discussion, there were 2 sections about the estimation of density. One section was about estimating for stationary conditions, and the other one was for estimating for non-stationary conditions. So for stationary conditions, we can use rho equals to Q over V. Actually, let me scroll up here and show you that part. So we have rho equals to Q over V, and we also have an additional factor that would consider the non-stationary conditions. So let's see. So this is for the non-stationary conditions. And we see this formula where we have the traffic density equals to flow divided by arithmetic mean speed, or it could also be harmonic mean speed. And then we also consider the covariance between the speed of individual vehicles and the time headway that they are keeping from the lead vehicle. And if we don't use covariance and instead use the correlation, linear correlation, then the formula becomes this. So since in the question they mentioned that there is no correlation here, we don't really need this factor anymore. It turns out to be 1. So we then get Q or V only, and that's exactly what we use here. Once we have estimated Q and V, we just take that hydrodynamic relation and then multiply it with 3.6 to convert it into the number of vehicles per kilometer for density. So if I run that, actually I did not run this, I think. Let me see if it is working. And now looking at the result, here we get, let me also increase the size here. So here we get for lane one, the speed is 25.8 meters, kilometers per hour. Sorry, no, it is still meters per second. It's in the same units as our problem. So that was on page 75. Yeah, it's still in the same units of meters per second because we did not use any conversion factor for the speed here. And then the speed in the second lane, which is the left lane, is 34 meters per second, which is expected because it's the left lane. And then for flow, we see a higher flow in lane one and a lower flow in lane two, which is left lane. And the density is 7.74 vehicles per kilometer in lane one and only 3.92 in lane two. So let's see the solution here. The solution also gets us the same values for the flow, 720 and 480, and the speed, 25.8 and 34. In part two of the question, we do have 7.74 and 3.92. So we do get the same answers based on the hydrodynamic relation that we have discussed before. Any questions so far? Next question is about determining the flow, speed, and density of both lanes combined. So naively, if we estimate the average flow, speed, and density of both lanes combined, you would just take all the vehicles and take the average of them, the speed of them, and then that would be the average speed of both lanes. But in the discussion, they mentioned that that is not true, and that is because of the discussion of the extensive and intensive quantities, which was, I think, the part of the discussion in the first chapter, where they mentioned that extensive quantities are those which depend on the vehicle number, and intensive quantities are those which do not depend or do not increase, as mentioned here, with the vehicle number. So flow and density, these are both extensive quantities. We can just simply take Q1 and Q2 from both lanes, add them, and that will give us the total flow. Similarly, we can do the same thing for the density, and that will give us a total density of 11.66 vehicles per kilometer. But for the intensive quantity speed, which does not increase with the vehicle number, we won't naively just take all the vehicle speeds and then take an average. Instead, we will depend on the hydrodynamic relationship, which is the Q total and the rho total. So again, we use that formula, and without considering these two steps, this is what we get as 28.5 meters per second. Instead of taking all the speed and taking the average, we use the hydrodynamic relation. In the discussion below, they mention that this is also the harmonic time mean speed, because if you recall from our previous discussions, this hydrodynamic relation is unbiased or relatively less biased when we use the space mean speed instead of arithmetic time mean speed. So this space mean speed, and particularly if it is the harmonic speed, then that is also an interpretation that we can do here for this estimation that we did. This is the time mean speed as well as space mean speed because it is estimated from the hydrodynamic relation. Now let's also discuss these two parts in the solution. In this first part, they consider flow as a combination of the density into speed, again, the hydrodynamic relation for the first lane and then for the second lane, and then added that to get Q total, which is the value is given to us as 1200 vehicles per hour. And then in this relation, here they consider the total density as, again, with the hydrodynamic relation. So what these steps show us is that there are different ways to interpret this macroscopic speed. You can consider the density, or the flow is a function of density and speed, or you can say the density is a function of flow and speed. And because when we consider density, we are only looking at a particular uh, point in time, and for flow, we are only considering a particular point in space, then the definitions vary. For a particular point in space, we are not considering the space mean speed, we are looking at the time mean speed. And the opposite for when we are looking at particular point in time, that would be the space mean speed. So that is why there are two interpretations of this speed that is estimated in this answer. Any questions? The final question here is what percentage of the vehicles in the right lane and in total are trucks? For this, we need to look at the data itself. So let me first clear this filter and then look at the speeds and also the vehicle length. So we see vehicle length here is 12 meters and then 15 meters, which are pretty long compared to other vehicle lengths. So these are trucks. So out of these 10 vehicles in the data, two are uh, trucks. So if you look at all of the lanes, both lanes, then this is 2 out of 10. If we only look at one lane, then in both cases, these are trucks driving in the right lane, lane number 1. So in that case, it would be 2 out of 6 because there are 6 vehicles in lane 1. So based on that, we'll get this as the percentage for trucks on the right lane alone. And then that's 33.3%. And then this is going to be 20% for the overall both lane based percentage of trucks. Okay, any questions about this section before we go to the second one? All right, let's move on to the second part of the exercise. Here it says determining macroscopic quantities from single vehicle data. On a two-lane highway, all vehicles drive with distance headway 60 meters. The vehicles on the left lane all drive at speed of 144, and on the right lane, it's half of it, which is 72. A stationary detector captures single vehicle data and aggregates them using delta t of 60 seconds. So this is the problem that we have previously seen when we were discussing the chapter. The only difference from this example is that in the example, they used 120 meters of distance headway in the left lane. So whatever was happening in the right lane, we doubled it for the left lane in the example. But in the exercise, they have made one distinction. In the exercise, they are saying that all the speeds of the right lane vehicles is still 72. All the speeds of the left lane vehicles is still 144, but the distance headway remains the same. It remains at 60 meters, not only in the right lane, but also in the left lane, which is mentioned right here, the distance headway of 60 meters. And we are also told that the aggregation interval is 60 seconds. So the first question here says, what are the time headways delta ti on both lanes? And what are the time gaps, assuming all vehicles are 5 meters long? Because we are given the distance headway, it's not too difficult to estimate the time headways, also given that we have the equations for this. So if we go to the beginning of the chapter, let me go to cross-sectional data. And here we have the definition of the time headway as well as the distance headway. So the distance headway tells us that the equation is the speed of the lead vehicle into the time headway. We want to estimate the time headway as per the question. And for that, we also need the speed of lead vehicle. We know all speeds are given to us. They are the same for both lanes. Um, individual lanes have individual speeds, but by lane they are the same. And distance headway is given to us as 60 meters. So all we need to do is just use equation 5.4 to estimate that. So let's go to the solution. And right here in question 1, we do see the time gap of distance headway of 60 meters divided by the speed of 40 meters per second, which is converted from 144 kilometers per hour. And that turns out to be 1.5 seconds. And then we do the same thing for the right lane. Here, the speed is half of the left lane, which is 20 meters. But note that the distance headway remains the same of 60 meters. And so we get 3 seconds of time headway. Okay, let's go back to the question. So the second part of the same question is, what are the time gaps, assuming all vehicles are 5 meters long? So for time gap, we have um, time headways already. For time gap, we need to first look at the equation for the time gap. Time gap, capital T, is equal to delta Ti minus Vi divided by Li minus 1. So there's a mistake here. This is not, we did not capture this error in the book when we were discussing it, but there is a mistake here. This is actually a full line here. So we have in the numerator the time headway minus the speed of the lead vehicle divided by the length. That's at least how they have interpreted it in the solution. So if we now go back and then use that, here we are for the time gap. They have taken the delta Ti, which is the time headway, which is, sorry, this is in this case the distance headway, minus the length, which is Li minus 1, the 5 meters length, which is given to us, and then the speed is 40 meters per second. I actually made an error here. This is the distance headway, not the time headway. So instead of using this equation directly, what they've done is they've taken the distance headway and subtracted the length from it, and then divided it by um, the speed, which makes sense because the time gap between the two vehicles from the rear of the lead vehicle's bumper to the front bumper of the following vehicle, that's what is the time gap. So for this time gap, we want to look at the distance that is covered, which does not include the length of the lead vehicle and the speed at which the vehicle was traveling. Based on that, we can estimate the time gap. So that turns out to be 1.375 seconds for the right lane and 2.75 seconds for the left lane. Actually, the opposite, 2.75 seconds for the right lane. It is slower, so we have a longer time gap. Okay, any questions here before we move on to the next part of the question? All right, so this part is done. Next part says find the traffic flow, occupancy, and average speed, both arithmetic and harmonic timing, separately for both lanes. That is, each lane is captured by its own detector, and also for both lanes combined. That is, one detector captures vehicles on both lanes. Let's look at the solution. So for the macroscopic quantities, they are saying that we are assuming an aggregation and time interval of delta t of 60 seconds, which is given in the question. However, due to the stationary situation considered here, any other aggregation interval will also lead to the same results. Directly from the definition of flow, occupancy and time mean speed we obtain for each lane. So here we have the definition of the flow. We have previously seen the definition of the flow is number of vehicles divided by the time interval, but we can also estimate it as the average of, the reciprocal of the uh, time headway, the average of the time headway. So 1 divided by expected value of time headway, that is how they explain it in the chapter. So since all vehicles are moving at the same speed, the average time headway is also going to be the same, which is 1.5 seconds, which we estimated in the previous answer. So we use that and we get 2,400 vehicles per hour in the left lane and only 1,200 vehicles per hour in the right lane. And that's because vehicles in the right lane are slower, so the flow is also smaller. For the occupancy, if we go back to the definition, it is the fraction of time that vehicles are observed on the detector out of the aggregation interval. So the aggregation interval is 60 seconds. Within 60 seconds, how much of the time were the vehicles on the detector? But in this case, we can also interpret it as when only one vehicle is on the detector, we know that the time gap in the left lane is, sorry, not the time gap, the time headway in the left lane is only 1.5 seconds. So there is one vehicle on the detector. After 1.5 seconds, there will be another vehicle on that same detector. That is our time headway. Within that, we are looking at the occupancy. So in that case, they then plug in 0.125, which is the number of vehicles that are going to, actually, sorry, it's not the number of vehicles, it is the amount in time when the vehicle will be on it. We know that the length is 5 meters and the speed is 40 seconds. So if we take 5 meters, 5 divided by 40, that comes out to be 0.125. So one vehicle in left lane, which has a length of 5 meters, is going to be on the detector while traveling at a speed of 40 meters per second. This is the numerator that we get, 0.125. Length, which is meters, and divided by meters per second, we get the time for which the vehicle is going to be on that detector. So one vehicle is on the detector for 0.125 seconds, and the time headway is 1.5 seconds. Based on this definition of occupancy, we get a value of 8.3%. And it turns out to be the same value for the right lane as well, where again it's 5 meters divided by 20 meters per second. That comes out to be 0.25 seconds for the occupancy on the detector by one vehicle. And for the speeds, we get the speed of 144 kilometers per hour and 72 as the macroscopic speed, which is already given to us. So that is for individual lanes. For both lanes, again, what was discussed before, we take the summation of the flow and both lanes have the same occupancy. And then we take the arithmetic time mean speed and also harmonic mean speed formula for getting the overall speeds. For harmonic time mean speed, if you notice here, sorry, not the harmonic, the arithmetic time mean speed, if you notice here, we have 40 vehicles that are passing at a speed of 40 meters per second. How are they 40 vehicles? It's because of the time interval. The time headway is 1.5 seconds for left lane and 3 seconds for the right lane. In 60 seconds, 40 vehicles would pass given 1.5 seconds of the time headway. In 60 seconds, 20 vehicles would pass the detector in 60 seconds when the time headway is 3 seconds in the right lane. So we do that for all vehicles, we get their speeds, and then we divide it by 60 vehicles, 40 plus 20, and that turns out to be 120 kilometers per hour. We do the same with the formula of the harmonic time mean speed, and we get 108 kilometers per hour. So we find that the arithmetic time mean speed is higher than the harmonic time mean speed, which the chapter has mentioned multiple times is going to be the case based on the Lorentz-Bach relationship, which was discussed in previous chapters. And the key takeaway there is that arithmetic time mean speed is always going to be either equal to or higher than the harmonic time mean speed. All right, I know I'm going very fast, but that's because there's a lot of questions to cover here. Any questions before we go on to the next part? All right, so point number three, besides two mathematical methods of averaging arithmetic and harmonic, there are also two physical ways, temporal and spatial, for which type of physical averaging does, in the concrete situation, the following statement hold. The arithmetic mean speed on the road is equal to the simple arithmetic mean speed of the two lanes. If you recall from our previous discussions across the chapters, we know that there are different ways to estimate speeds. There is a temporal speed, there is a spatial speed, but there's also the arithmetic mean speed, and there's also the harmonic mean speed. So there are different ways to estimate both temporal speed and spatial speed, either using arithmetic mean or harmonic mean. The question here says, in what condition is this statement true? The arithmetic mean speed on the road is equal to the simple arithmetic mean speed of the two lanes. When will this statement be true? So let's see the solution. So here they say in traffic flow, there are four sensible ways to average, consisting of the four combinations of one of two physical ways, time mean and space mean, and one of two mathematical ways, arithmetic mean and the harmonic mean. Time mean means averaging at a fixed location over time interval as done by stationary detectors. Space mean means averaging at a fixed time over some space interval, which means the road section, for example, when making a snapshot of the traffic flow. So if we have like trajectory data, then we can estimate space mean speed reliably. So for the space mean, they then use this equation, which was also discussed previously in the previous question right here. And that's why the interpretation was that we can estimate both the space mean and the time mean. So for space mean, we can use density because density depends on number of vehicles divided by the space interval in which the vehicles were observed. So it could be 1 kilometer, for example. And for the time mean, we consider flow, which is only looking at one cross section, but for the time interval of delta t. So we can estimate in both ways. So here they say the answer to that question is here the density in lane one is equal to the density in lane two, but their flows are not equal. So the simple arithmetic average over lanes applies for the space mean speed. So that statement will only be true if we are estimating the space mean speed. The statement again was the arithmetic mean speed on the road is equal to the simple arithmetic mean speed of the two lanes. This arithmetic mean speed will be the space mean speed. If we have our hands on that, if we can estimate the space mean speed, then the arithmetic mean of the two lanes is going to be simple arithmetic mean of those two lanes space mean speed. In that case, this statement will be true. Okay, any questions here? I think for us, because these are the things that we can easily forget, the key takeaways are that we can estimate speeds in different ways, and we need to see where it applies. It mainly applies to hydrodynamic relation. Whenever we are estimating or using the hydrodynamic relation, which is density is equal to flow divided by speed, then that speed, if we have space mean speed, we are getting reliable results, better results less biased results. But if we are using the time mean speed, using only the arithmetic time mean speed, and it is yeah, using the time mean speed as the concept in the traffic flow, then we may have some bias in our estimations. So I think the key takeaway is space mean speed is better whenever we are using the hydrodynamic relation. Question number 4 is about calculating the speed variance. So speed variance has this formula. I'm going to skip this in the interest of time. But speed variance simply means what is the variation in the speed, because it is a distribution of speed. We have looked at the macroscopic mean speed, but there's also the variation in the speed. So if you want to later discuss it, we can. But in the interest of time, sorry, I'm going to skip it. Question number 3, analytical fundamental diagram. And this is the favorite one in all of these exercises because we can do some actual like practical thing here. Derive and sketch both the speed density diagram and the fundamental diagram. Speed density diagram and the fundamental diagram. Let's first review what those things were very quickly. So it's actually pretty close to the end of the chapter. Let me go back here. And so here we have the speed density diagram and also the speed flow diagram. And if we actually have fitted lines on the data, for example, we have this one where we have flow on the y-axis and density on the x-axis, and we have these lines which are based on fitting the mathematical model onto the data points. Then these lines are called as fundamental diagrams. This is essentially the flow density diagram if we have data points, but we will call it fundamental diagram if we fit these lines. So the question is about estimating them given the data here. So here we have some assumptions. Assumptions are all vehicles are of length 5 meters. In free traffic, speed does not depend on other vehicles. All vehicles drive at their desired speed. Desired speed is given to us 120 kilometers per hour. In congested traffic, speed is the same as the speed of the leading vehicle. Drivers keep a gap of S naught plus VT. S naught is the minimum gap, which is 2 meters, and capital T is the time gap, which is 1.6 seconds. Given these things, we need to derive the speed density diagram and fundamental diagram and also sketch them. Okay, so let's go to the solution here. This is 5.3. So here they say, because we have these two parts of the diagram, and let's keep that diagram in front of us so it makes more sense of what we are discussing. I'm going to just take a screenshot of it here. So we have these two parts. We have this line that represents the free condition, the free flow conditions, and this line which represents the congested conditions. So we need to sketch this. We also need to derive it given the data to us. So let's move on to the data again. And then look at the solution. First, free traffic. For free traffic, we have v free as the desired speed, which is a constant. So I've put all of that here in question 3. The length of the vehicle is given, which is 5 meters. Speed is 33.33 meters per second. In kilometers per hour, it is 120 as given to us. The time gap and the minimum space gap are also given to us. And then we have these formula for the density, etc. So let's continue the discussion from the solution here. So for free traffic, we know it is a constant. Flow For the free traffic, we can estimate using the hydrodynamic relation. So flow is going to be density into the desired speed. So if we go back and estimate that, here is the free traffic section, and we have the I made this as a function as one that takes in the density and already has a desired speed as the value which is given to us. So in this case, remember this formula, density or rho into V naught. That's exactly what I'm doing here. We are giving it rho and the desired speed, multiplying rho with the desired speed. And then we need to estimate this that I do here. But before I show you how this is working, let's read further. For the congested traffic, the speed-dependent equilibrium gap between vehicles is given to us in the equation. In the question, it leads to the gap-dependent equilibrium speed. That turns out to be congested speed is going to be S minus S naught divided by T. Why are we using this equation, which is for a single vehicle speed using macroscopic speed? How are these two equivalents? Can anyone guess why this v, small v that represents a single vehicle, can be replaced with the macroscopic speed in congested conditions? Any ideas? The reason is that it is we are assuming that we are in the steady state equilibrium conditions or the stationary conditions. Just to review, stationary conditions are those where we assume that all vehicles will have the same speed distribution over time. Over time, it does not change. If the aggregation interval, for example, is 60 seconds, within those 60 seconds, the speed distribution, if it has a speed a mean and uh, standard deviation, that is not going to change. It's going to be the same within that delta t. So that's exactly the assumption here. For the fundamental diagram is based on steady state equilibrium conditions. So conditions are not changing. That's why we can say all vehicles at the same speed, so their macroscopic average will also be the same. So that's why we can just use this equation to estimate congested speed. And for the density, we use the formula of number of vehicles per road length. And that turns out to be 1 divided by the length of the vehicle plus the distance gap. So 1 divided by L plus S. And then when we plug in this thing for density, right here, 1 over L plus S, sorry, here in this equation, we have S. And S is equal to 1 over rho minus L. And why is that the case? We have previously discussed that there is a relationship between flow and the time headway. Flow is equal to 1 divided by average of the time headway. Similarly, the density is equal to 1 divided by average of the distance headway. So based on that, we can estimate the distance gap. Remember, this is distance gap, not the distance headway. Distance headway has a notation of delta, sorry, di. So di is 1 over rho minus the length of the vehicle, we get s, which is the distance headway, sorry, distance gap. So using this, when we plug in s equals to 1 over rho minus L, and then we plug in that in this equation, the congested speed can be estimated using this equation. And then the flow density relation can be estimated by estimating flow, which is again equal to rho into V. In this case, V congested and that turns out to be this. The maximum density is going to be wherever the distance gap is the smallest, which is S naught. So 1 divided by L plus S naught, which we also call as L effective. And then the critical density is that density where the flow is the highest. After that, the congestion starts. In our figure here, this is the point of the maximum flow, which we also call as capacity C. And the density corresponding to that is going to be critical density, rho sub C. So again, plugging in those formula in this formula of rho into V naught into T, we get, actually in this case, the assumption is that congested uh, flow is going to be equal to the free flow when we are talking about capacity C. At this point, on the left is the free branch, on the right is the congested branch. At this point, both the flows from the two equations of free and congested conditions are equal, which is equal to C. So if we equate them using their equations that we have derived above, we then get this formula for the critical density. And the capacity is again the flow in the congested conditions, which we already have a formula for. We then estimate that for the maximum flow, which is using the effective length, which is essentially equal to L plus the minimum gap. So based on all of these equations, these derivations, we can now plug in these in R and then estimate them for some hypothetical values of density. So in this example, we have the hypothetical examples from 0 to 120 vehicles per kilometers per lane. So if we do that right here, and using all those formula for the rho max, rho critical, and then capacity, we can then estimate, actually sketch the fundamental diagram. So we do that here, and then using the Q free. In this case, when we look at the critical density, it turns out to be 0.016 vehicles per second, sorry, per meter. And if you look at the example here, where I have taken from 0 to 120, this is going to be the input values of the density. 20 is, if we convert it from vehicles per kilometer to vehicles per meter, 20 is going to be 0.02, which means that the first two values here, these correspond to this thing. These first two values are for the density in free conditions, and the remaining values are for the density in the congested conditions. This is based on the critical value, which is again based on the derivation, which is done here. So based on this formula, the critical density where the flow is the maximum is 0.016, which is smaller than 0.02. So we consider that these are the first two values for free conditions, and then after that, it is congested conditions. Okay, so if we have all those values, let me make sure that I'm running all of them. So I'm just simply using those equations that were derived in the solution. And then if we plot these things, this is the result of looking at density on x-axis and the flow on the y-axis. So this is the fundamental diagram because this is flow density diagram using the assumption that this is steady state equilibrium. So this is very much like what we see here, a triangular fundamental diagram. And then if we do the same thing for the speed speed density plot that turns out to be this thing. For some reason, I don't know why it's showing the line here, but not here. But that also gave us a similar result compared to the example in the book. So right here, if we go to the final question here, this is an example of speed density diagram. And now look at our solution here. This is speed density diagram, which has the same relationship. Initial desired speed is higher, and then it reduces when density increases. All right, any questions here before we go on to the next part? All right, question number 4 is about estimating the velocity of traffic waves. And here they have given us one example. We have 3 detectors, and these detectors have speed and time for us. So the black line represents the detector at D07, and the orange one is D09, and in between is D08. The difference between them, at least between 07 and 09, is 2 meters, 2 kilometers, sorry, which is highlighted here as well. So at around 8, 8, 8, I think, uh, we have the detector value, the speed value for D07, and at around 805, I think, we have the detector value, uh, sorry, the speed value for the detector D09. So they're showing the same pattern. They're showing us that the upstream detector is D07 and the downstream is D09. And so we see the speed decreased in D07 first, and then um, actually it is 473 kilometers and then 475. So in that case, D07 is the um, upstream one, and D09 is the downstream one. So we see at almost 8:05 a.m., we have the speed of 0, and then the same pattern happens in D07. This is based on the example we have previously discussed. So let me quickly get to that example right here. So D07 is here, it is the upstream one, and D09 is here. So vehicles are traveling from bottom to top in this figure. So this is the upstream and that's going to be downstream. And so we see the speed at DO7 as well as at DO8 and DO9. So right here, the black one is DO7, the orange one is DO9. And so the questions here, and I'm going to quickly cover this because we don't have a lot of time left. But the question is about wave velocity. How do we estimate the wave velocity? For this example, in the discussion in the chapter, they tell us that you can just look at the distance between them and divide it by the time uh, between the same points. Whenever we have the same pattern, we identify those patterns and then see what is the time difference between them and what is the distance between these 2 detectors. Based on that, we can estimate the wave velocity. So if we look at that here for D07 and D09, uh, they tell us that the difference between them is 2,000 meters or 2 kilometers, and the delta t is 450 seconds. This is based on what is highlighted here. If you convert this time into seconds, that turns out to be 450 seconds. So we take the delta x, which is 2,000 meters, we take the delta t, which is 450 seconds, and the wave velocity turns out to be minus 4.44 meters per second, which means that from downstream to upstream, we have a traffic wave which is moving upstream, and that is why this is negative. and the speed of that traffic wave is 4.4 meters per second. Okay, now we have the final question for today, which is fundamental diagram estimated from stationary detector data. Considering the flow density diagram of figure 5.14, this one, and the flow speed following speed density diagram, which is given here, average over all lanes of the German A8 East and the Dutch A9, determine the desired speed V naught, time gap T, maximum density rho max, and the capacity drop on both highways from the fitted curves. Which statements can you make about the driving behavior of German and Dutch drivers? So let me zoom in a bit and let's first talk about the behavior of the drivers here. So let's look at the desired speed first. So what do you see is the desired speed? We can see the maximum speed here for the German road and for the Dutch road. The solution also mentions that Dutch police is very strict in enforcing the speed, so that's why we never go above, in this case, as I see it, 105 kilometers per hour. And for the German, it's about 125 kilometers per hour. So that's the desired speed. And then uh, we also have a maximum density here. So we can estimate the maximum density either from this plot or from this plot. For the German one, we see it's 80 kilometers vehicles per kilometers per lane, and then for the A9, we see it's about 110 vehicles per kilometer per lane. Then the question is about the time gap and the capacity drop. So we do have flow here from this plot. We can estimate what the flow is for both. And based on that, we can estimate the time headway because flow is equal to 1 divided by average time headway. Once we get the time headway using the flow values, we can then also estimate the time gap. So let's see what the solution says. So here they say the free velocity can be read off that speed density diagram, which we previously saw, 125, 110. And the flow density diagram immediately shows the maximum density and capacity. So we have also estimated 80 and 110 from the plot. And here's the capacity, 1700 vehicles per hour and 2400 vehicles per hour. So if you see here, this does seem to be 1700 and 2400 because that's the maximum flow. So that is the capacity. And the headway is then estimated using the formula that we have discussed in previous discussion. I think it was 5.2 or 3, where we had this formula for the time gap. And so using this formula, where we're using L effective, which is length of vehicle plus the minimum gap, the capacity, and the desired speed. C is again here as capacity. Rho max can be used instead of L effective. So we use rho max, which is given to us from the plots. Using this formula, we then get the time gap of 1.9 seconds and 1.27 seconds. So the Dutch A9 time gap is smaller. Sorry, A9 is which one? A9 is, yes, it is Dutch. It is smaller time gap compared to the time gap of uh, German road, and that's because they have higher flow. All right, so that completes the answers, the exercises for this chapter. The next chapter is going to be about spatio-temporal determination of the traffic state. And as I mentioned before, it is going to be the last one in the traffic data part. And then we'll start with traffic flow modeling after this chapter. Any questions before we finish off today? Okay, thank you so much for attending, and I'll see you next week.